Well, it's an honor and a pleasure to be here at LambdaConf. As the title indicates, I'd like to talk about robust parsing, whatever that is, and novel markup languages. And I'll explain these terms as we go along. So there's a context to this, which I have to make this confession. I am, by choice, a mathematician, and I spent most of my career as a math professor. And one of the things that we often do is we write up course notes, problem sets, solutions to the problems for the students. And if we were doing programming, we'd just use Markdown, which is a great markup language. But we have equations to deal with, so we use LaTeX instead. And LaTeX, the typical way of using it is you have your document, which you have a text editor, and you run PDF LaTeX, and you get some errors, and you correct those, and you get a PDF file at some point, and then you keep iterating this procedure. So it's a somewhat exhausting workflow, okay? But the endpoint is a PDF file which you can print and distribute in class, or you can post it on the web for your students. And of course, we use this for our research articles as well. So that's the context in which I'm working. And these days, what students really want is a web document. That's what they're used to. They can read it on their phones, they can read it on their computers, any device in between, okay? And so I thought, well, maybe there's a better way of doing this. And so this mini screenshot here is an attempt at that. So you see two windows there. The one on the left is a text editor. The one on the right is the rendered text. And the idea is that as you type, the source text should be instantaneously rendered in the right window. Now, if you have instantaneous rendering, then you also have another problem, which is your document will frequently be in an error state because in tech, you would say backslash something or other, open curly brace, and suppose you forgot to put the closing curly brace. Well, various forms of bad things could happen to your rendered text. And so if you're going to have an instantaneous rendering system, you've got to have a graceful way of dealing with these syntax errors. So I'll give you some examples here in a moment. But so the idea is that if you want to have a really good way of creating documents on the web, a web native solution, then you also have to solve this robust parsing problem. And so I've been working on this for a while, and for whatever reason, my system, which is this one here, scripted.io, it can handle 3 different markup languages. I began with LaTeX, or my little version of it, micro LaTeX. And then a friend of mine said, well, Jim, you really ought to do Markdown because you might get more users that way. So I did that, and I built in some extra features to my little version of Markdown so that it can handle equations. And there are lots of things like that out there on the web. And then, because I really didn't know anything about robust parsing, I designed a very, very simple markup language, which I think in the announcement, which goes back several years, when LambdaConf didn't happen, I called it L0. And I now call it enclosure for various reasons. But it's a bare bones, simple, but yet surprisingly expressive markup language that I use as a test bed for these ideas of robust parsing. And when I get into the explanation of what robust parsing is and how you implement it, I'll use this enclosure language as for the examples, but the same principles apply to everything. So a little personal story, I've been fiddling around with programming all my life, even though I'm a math guy. And I began, in relation to the previous talk, punching cards for Fortran, and eventually fiddled around with lots of other languages, and I thought, okay, well, if I've done that, I can learn how to develop a real web app. Of course, I found that was actually much, much harder to do, and it's taken me quite a while. So this app is written in a statically typed pure functional language called Elm, and it also relies on a framework called Lambda, which allows me to write Elm on both the front end and the back end. And for me, as a solo developer in this project, it's a big win because it lowers my cognitive load. I don't have to deal with two languages simultaneously. And also the problem of migrations is very transparent. Okay, let's look at a screenshot in a little bit more detail to see what the problems are. So on the left, this is a blown up version of the previous one. On the left, you see a markup language, happens to be micro LaTeX. And let's concentrate on this little piece of it. Can you read that text there? It's not huge, but okay, great. So if you read it, it says, a key feature of such packets is their backslash term, curly brace, group velocity, and some other stuff, okay? And the corresponding rendered text is what you see on the right. You'll notice that backslash term curly brace is rendered in pink. That indicates there's an error there. Now, so that fulfills one of the goals of robust parsing, okay? We make note of the error in some graceful way in the rendered text. And you notice another thing, if you look at the rendered text, you see this little V subscript G. So that's a little piece of math text. And if you look at the corresponding thing on the left in the editor, you see $V $_G$. So that's how you do inline math in LaTeX. And so the important thing to note is that after this error, you have some more markup, but it's correctly rendered. Okay, so that again is that's the other goal for robust parsing. And of course, if you look at the little thing that I've highlighted up above, that's how it really should be rendered. Okay, so backslash term is in tech language, it's a macro. I think of it as a function whose argument in this case is group velocity. So my point of view on this is that running text in a document consists of expressions of various kinds. It might be pure text, it might be a function expression, or maybe there's some other kind of expression. But the idea is to keep the number of types of expressions very, very small. Let's see, let me try getting that back. Okay, Okay, there are a couple of other things to notice here. One is that the text is structured as a bunch of blocks, ordinary paragraphs, and other things. And the one, we already saw that, the design goals. Instantaneous rendering, robust parsing, okay? There's one other kind of block, which is this begin equation thing that you see here. In LaTeX language, that's an environment. I call it an equation block. And those kinds of environments always begin with \begin, and then the name of the environment in curly braces, and the corresponding ending tag. And of course, another kind of error you can have is that if you mess up the ending tag, or if you just forget it, then you can have various forms of garbled text in the rendered version of the document. So you have to do some kind of robust parsing, not only on the level of the running language, but also the blocks. So I won't say too much about that, but it is a problem, and it's handled using the same kind of logic that I will describe for handling the so to speak, the internal language. Okay, so, and that, of course, is the text that is rendered from that. Okay, so let me do a couple of quick demos, and then I'll get into the mechanics of writing a robust parser. So the first one, assuming that I have a web connection here, and I do, very good. Okay, so this is a little handout written in micro LaTeX, and let me show you a couple of things, because there are really two parts to this talk. One is the mechanics of robust parsing, and the other is building a system that users will find useful. So one thing you can do is you can search for stuff. So I'm going to search for art, abstract, and hopefully it will find it. Yes, there's something on abstract art. And this is just a little notebook of images that I happen to like. And if I open up this little open book icon, it gives me a live index into those. So if I want to know what Amy Stone painted, there it is. Okay. So you can do lots of things besides math and physics with this also. But let's go back to the demo. This little button up here allows you to edit the document. This one copies a link to the document into the clipboard so you can post it on the web someplace or send it to your friends in an email. Say, hey, read this stuff. This little button will turn the document into a PDF file. So I press it, it says, please wait. Now it says click for PDF. and there's the PDF. And I'll describe later how it did that. Okay, but it does it. The name of the author, I think that's all I want to say there. Okay, let's now edit the document because I want to convince you that it really can render things instantaneously. So what did I do? I clicked on some of the rendered text. It opened up the editor, and the paragraph that I clicked on is highlighted, and so is the corresponding rendered text. So an important thing for providing a good user experience is to be able to go back and forth between the source text and the render text in a convenient way. And in order to be able to do that, your parser has to build some stuff into the syntax tree that makes that possible. Okay, so let me do one thing that's pretty easy here. You see where we have the error. I'm going to just put a right curly brace there, and the error disappears. You saw that? Okay, I'll remove it. It's there in pink. I'll put the curly brace back in. It's fixed it, okay? So, of course it's not instantaneous because that's physically impossible, but it's fast enough for us human beings. Let me give you a slightly more dramatic version of this. I'll cut out all of the document except the title, and now I'm going to paste it back in. 3, 2, 1, 0. Okay, so it's essentially instantaneous, okay? Now, I think that's enough on micro LaTeX. So let's go back and take a look at the other demos. I think I'm going to skip the markdown one. Let's do it. We'll just do it very fast, okay? By the way, what I'm doing is I'm clicking on those kind of links that I said that little link icon will give you, and they link directly to the document, and they'll open up it in guest mode, so you don't have to be a user of the system in order to benefit from it. So for students, for example, this is important. They may not want to register and go through all that hoopla. Okay, so let's just cut right to the chase. If I open up the table of contents, it works. So, and I didn't write any particular code in there to make that happen. It's just a feature of the system, okay? If I click on the rendered text, it opens it up, and what do you see? The usual kind of markdown stuff, like introduction begins with a hash mark, because that's a new section. And then, of course, we see some math text, like that, okay? And that looks almost like valid LaTeX code, but it's not because there's no trailing double dollar sign, okay? And, I decided that that's not really necessary because the way I view blocks is they can be terminated by a blank line. So if you adopt that approach, then you immediately eliminate one class of errors, namely errors coming from missing trailing block terminators. As you know, there's more to life than mathematics, so down here is a little chemistry example. The reaction that produces water from hydrogen and oxygen, along with an explosion, small or large, depending on how much of those gases you have. Okay, last little demo. Let's go to the enclosure one. So at the top, there's some demo stuff, and I want to look at that because that gives you a complete view of the syntax of this little language. Okay, so let's look at just this stuff right here. Okay, so we don't need to look that up in my dictionary. Okay, so if you look at that, then what is it that you see? Well, you see, first of all, vertical bar, I'm just going to say pipe, okay? You see pipe, space, section, demo stuff. That's what I call an ordinary block. Okay, so it begins with pipe space. There's a name for the block, in this case it's section. There could be some arguments, but in this case there aren't any. And then there's the body of the block, which follows that. That's a bunch of contiguous non-blank lines, terminated by a blank line. Then we have another block, which is just a plain old paragraph, but it has some markup in it. And if you look at the markup, you see these are what I call function expressions. That's a text expression. It's followed by let's look at this one first. Red hot chili peppers in braces, in brackets. So a function expression begins with a bracket and ends with a closing bracket. The function name is red, And you see what it does over there. It makes its argument, which is the rest of the stuff there, it turns it into red text. Here we have a more elaborate function expression. The function I is applied to several arguments, really, and then this other function element that makes the word strong be bold. Okay, so function elements, just like functions that you use in mathematics, can be composed. Okay, in the next line, you see a math expression. So these are what I call verbatim function elements. And the difference is, well, there's a syntactic difference, but that's not the important one. The difference is that regular functional elements, the arguments are parsed. In this case, the argument, this Pythagorean formula, is not parsed. It's passed directly to the rendering function. Okay, so here's another ordinary block. And then finally, an equation block, which renders this nice little equation here. Equation blocks are different in that they begin with a double pipe, and like verbatim functions, the body is not parsed. It's passed directly to the renderer. Okay, so there's one other thing I want to show you here. So these are some notes on type theory that I may talk about at some point, but not here. But notice it has lots and lots of sections. Okay, let me go to the very end, and let's look at this formula right here. So I'm going to select it. I didn't do quite the right thing here. Just to say, let me go down here. I'm being a bit clumsy here. Let's look at, where is it? I'm having trouble reading my own text, which is really bad. Okay, here it is. Okay, so you see that blackboard bold N, which is right there. Okay, where did that come from? Well, it came from this source text \nat. And this is a reflection of the fact that mathematicians are lazy people, and I don't want to have to type out \math BBB curly brace in close curly brace every time. So instead, what everybody who uses LaTeX does is they define macros that are essentially abbreviations for those things. So there's a macro definition. So Scripta will handle those as well. Okay, and let me show you a little thing that illustrates the rapidity of this, even on fairly large documents. This is a 13,000 word, 40-page document. Okay, so I'm going to cut out the macro definition. Notice what happened to the rendered text. All of those macro, every usage of the macro definitions is now an error. And now what I'm going to do is I'm going to paste it back in. So the entire document is going to be re-rendered, and your homework assignment is to see how fast it does that. So 3, 2, 1, 0. Okay, so again, it's pretty fast, okay? And I won't do this for lack of time, but I can cut out, as before, I can cut out the whole darn document and paste it back in, and you'll see the same thing. There's one other thing I guess I should do for you, which is let's turn this into a PDF file. So it says, please wait, click for PDF, and there it is. If you look up at the top, it is 40 pages long, okay? So, you know, I started this as an experiment, but actually I use this all the time in writing articles now because I just find it so much more convenient than LaTeX. It gives me this immediate feedback, which of course we all like. And I don't have to set things up, okay? Now, there are things I can't do. You know, there's never any free lunch. I can't import an arbitrary LaTeX package. So everything that has an advantage has some disadvantages as well. Okay, let's get into the brass tacks of things. We'll go back to the slides, and we'll see what we can do. Okay, so here's a diagram of the entire system. There's a lot more to such a thing than writing an HTML to a markup to HTML compiler, which is signified by the little green square that you see right there. Okay, in the pink box is the front end of the app, written in Elm. It communicates with the back end, also written in Elm, via WebSocket. So that is much more responsive than HTTP. okay? But there are other parts of the system that play a very important role. Above the pink box, you see two boxes. The left one is COTEC, that's what renders the math formulas. I could never have done this project if there were not a way already done for me to render math formulas. So it's a big JavaScript library. And although I'm not a fan of, I would never write a big app in JavaScript, but I'm very happy to use a well-written package in JavaScript that is basically, for me, a function. I give it something and it gives me something back, okay? I use CodeMirror, another very large and very nice JavaScript library for the editor. And I should say, you know, if any of you would like to collaborate with me, I am welcome to that idea. In particular, I've managed to make CodeMirror do some of the things that I would like it to do, but it's really pushing my abilities and my knowledge. If you look at the boxes on the bottom, you see, first of all, a PDF server. This lives in the cloud someplace. It's a 250-line Haskell program. And the way it produces PDFs is the following. Once you have the syntax tree, you can do all sorts of things. One is to turn it into HTML. But another thing you can do is you can turn it into standard LaTeX, that anybody can, you know, save it as a file, anybody can run PDF LaTeX on it. So that's what I do. I send it to this PDF server. It runs PDF LaTeX twice or maybe 3 times, I forget, and it sends back a link to that PDF file, and that's how you got what you saw. There's another little square which I won't say much about, but there's a little image facility in the app which allows you to upload images to Cloudflare, which then compresses them and sends you back a link, and that's how I put the images in the document. When they weren't already on the web, of course, where I could steal them. Okay, so let's now get into the nitty-gritty, which is how do you make a fault-tolerant parser, which is sort of necessary for any of this stuff to work. The parser has a pipeline. It's going to start with source text. It's going to turn that into primitive blocks, which are, a primitive block is a record that contains the content, the string representing those contiguous non-blank lines, and some metadata, like by how much is it indented, what's the name of the block, and so forth. Okay? That has to be turned into an expression block, which you do by parsing the content of that block, not the metadata, just the content. And that's done by the machine in this little pink rectangle. It takes the source text of the box, tokenizes it, and then runs a shift-reduce parser over it. The first version of this sort of stuff that I wrote, I did using parser combinators, which I must say I love. It's kind of like the way I think. But to do this robust error processing, error handling, it turned out I needed something more like a conventional shift-reduce parser. And then the last step is to turn the expression blocks into a forest of expression blocks. And the reason for that is that the source text contains information in the way that things are indented. You know this from Markdown, but you can do it in these other languages also. And so when you were in high school and you had to write an outline, you had major headings and subheadings and sub-subheadings. Well, that structure, your high school essay outline, actually has the structure of a forest, that is to say, a list of trees, okay? So I won't say too much about that until the very end, but it's important also. Now, another thing that's important is you'll see, we use a common syntax forest for all 3 markup languages. And this has many advantages. One of them is that, for me, it's a great one because, you know, I don't have the time to write 3 different renderers. This way I only have to write one. Write and test, I should say. Okay, so let's get into the parser. The tokenizer is going to take source text, turn it into a list of tokens. So there's the token type for enclosure. And the best way to see how it works is to look at an example. We'll use this example throughout in what follows. So there are 6 tokens. All but 2 of them are string tokens, S, and then the constructor is S, and the payload is a string, okay? The token at index 1 is a left bracket token. You see where that came from. The token at index 4 is a right bracket token, and you see where that came from in the text, there and there respectively. Okay, so that's the tokenizer, and we can all write one of those. What about expressions? Well, this is the type that is used for all expressions regardless of markup language. There are 3 variants corresponding to the constructor's text, fun for function, no fun here, just functions, vfun for verbatim function. And again, the way to understand the meaning of these things is to look at examples. The phrase in the beginning is parsed into the expression constructor text, string payload in the beginning. The phrase bracket bold stuff close bracket is parsed into the expression constructor fun, name bold payload, a text expression. And this math expression is parsed into a verbatim function because we're not going to do anything more to its argument. We're just going to pass it to the renderer. So the name of that verbatim function is math. The payload is the Pythagorean formula. And then, of course, it can handle more complicated things, of which this is a very small example. This gets parsed into a list of expressions. The one you see here, it has 2 things, a text expression and a function expression. Okay. So how are we going to implement this? Well, the idea is that the parser should eat tokens one at a time. And each time it eats a token, it needs to digest it and do something with it. And that the data that we have to keep around for it to do that is going to be contained in a value of type state. A value of type state is a record with 4 fields. There's a list of tokens, the ones you start with. There is an index, there's an index into the token list. That's the token that you're currently looking at. There's a stack of tokens that have been seen, that is to say eaten, but not yet turned into an expression. And then finally, there is a list of expressions that have been derived from the token list, okay? And we're going to process the token list using a function next step that, well, you think of it perhaps as taking a state and giving you a new state. But it's not quite that. It gives you a value of type step. And that's because of the way we implement loops in a functional language. So a value of type step has 2 possible variants, a loop variant and a done variant. So if the next step function returns something of type loop state, then it's going to recurse on that. It will apply it to it again. If it returns a value of type done, some other type, in our case it's going to be list expression, that's the signal that the loop is terminated. Okay, so there's the driver for the next step function. And the important thing to do is to look at this. What happens when you apply next step to the current state? Well, it either returns this or that. If it returns this, then we apply loop to t again, so that's the recursion. On the other hand, if it returns done with payload B, we just return that payload. Okay, so fortunately, we're not going to look at too much code because that's hard to understand in a real life situation. But here's I think the last real bit of code. So this actually is the code for the next step function, even though it reads like pseudocode. So let's take a look through it. So the way it works is we're going to try to get a token from the state. And the way we do that is we look at where does the token index point. If it points beyond the list of tokens, then it returns nothing. And if it can get a token, it returns just token. Well, let's look at the first case. If the stack is empty, then we return the expressions that have already been computed. How am I doing on time? Okay. Otherwise, we invoke a recover from error function. Okay. Now, the idea is that if we eat all the tokens and the stack is empty, we've succeeded in doing our job. Because remember, the way we create expressions is did I say this? We look at the stack and we try to turn that into an expression. Okay. So at the very end, I'll show you how the recover from error procedure works. Now, if we do get a token, we're going to transform the state successively by functions here, which take a state and return a state. So the first thing we'll do is something easy. We advance the token index. Next, we push a token onto the stack. So this is the shift operation of the shift reduce parser. And then we try to reduce the stack. Now, so here's where I say the important part. We look at the stack and we ask ourselves, does it represent an expression in this language? If it does, we construct that expression. We push it onto the list of expressions. We clear the stack, and we then pass this altered state into loop, and therefore loop again. Okay, so we look at the stack. If it corresponds to an expression, we put that expression onto the list of expressions, clear the stack, and keep going. It will frequently be the case, in fact, more frequently than not, that the tokens on the stack don't represent an expression yet, because if you start with a right bracket, you have to go at least until the first left bracket. I got it reversed. Start with the left bracket, you've got to go to a right bracket, okay? So if it says, okay, this doesn't represent an expression, then it just passes the state through unchanged, okay? So that's the outline, and I did this with my laser pointer now that I know how to use one. So let's now look at an example, because this is the way I figured this stuff out, is I did it all by pencil and paper, and then I wrote the code, okay? So there's some source text, there's the corresponding list of tokens, there is the initialized state value. E stands for expression, it's an empty list. S is the stack, it's an empty list. T is the token pointer, it's initialized to 0. And above it is the token list itself. So we're going to, first of all, we're going to run our machine by hand. Where is the token pointer pointing? It's pointing at the 0th token, which is this one right here. So what do? We shift that onto the stack, okay? Then we try to reduce it. And in this case, we can reduce it because that corresponds to a text expression. Okay, now what is pointed to by T? The left bracket token, so we shift that onto the stack. We ask, can it be reduced? Well, it can't, so we just pass it on. We continue. We try to speed up the machine a little bit. What is the token at index 2? Well, it's the string token I. We shift that onto the stack. Can we reduce it? Nope. So this is, like I said, we usually don't do anything when we reduce. But now we go to the next slide. The stuff in gray is what we've already done. The token index is 3. What is there? It's the string token strong. We shift that onto the stack. We can't reduce it yet because we haven't found an RB yet. Okay. String token 4, well, what's there? Does index 4. What is index 4? An RB. Okay, so we shift that onto the stack, and now we can reduce it because the previous line here corresponds, if we read from right to left, corresponds to a function element, namely this one right here. Okay, so that's the operation, and I don't know, I'll click through the next stuff at the speed of light because it's the same stuff. We do another shift, we do another reduce, and we get the whole thing, okay? So that's great, that's the happy path. Now, what happens if we have an error? So we should look at some text with an error. So we just use our previous example, but we delete the closing brace, or the closing bracket rather. And we want to parse it in such a way that the final result, when we render it, is this is bracket I strong stuff with bracket I rendered in pink, okay? So once again, by looking at examples, you are led to the right code to write. Okay, so we're going to take our machine, we're going to run it on the input text, and we get to this point, okay? We have, let's see, I guess we need one more thing. There we go. So we have computed one expression on the list E. The stack has a lot of stuff, but our token index is 4, and there's no token at index 4. So we reached an error state, and we have to invoke an error handling procedure. And we're going to do it as follows. Let me tell you what the idea is. So if we look at the stack from right to left, we see it begins with a left bracket and a string I. So that's the correct way for a function element to begin. So that's your clue. We have a function element that we couldn't complete. Okay, so what we're going to do is we're going to take this and we're going to cook up some valid expression that will render bracket I in pink. So what we do is this. We cook up the element fun, text pink, and then payload the text element left bracket I. Okay, so that will render as a pink left bracket I. Okay, and let's see. So what do we have on the expression list now? We have what we had before plus this error element. Okay, and now we do something seems drastic, but that's what we do. We clear the stack. We set the token pointer to 3. And why 3? Because you see we have, whoops, oh dear, I see I can use this. Oh, that's very interesting. Sorry, I'm a little bit of a noob at this stuff. Okay, so that's the button I want to push. You see, what are the indices here? Well, we have LB and we have the string token. So we've processed all this okay, and we have not, but this we still have to deal with. So 3 is the correct thing to reset the token index to. And what we do is we just restart the parser at that. So this is an extremely simple algorithm, but it has, well, one virtue it has is that it's guaranteed to terminate because you keep reducing the size of the token list that you handle. It also has the ability to handle, oops, oh dear, I did something to this, and I'm going to see if I can put it back on correctly. Yes, help is gratefully accepted. Okay, I'll try to not do that again. Okay, so so there are a few more steps. You have to eat up the rest of it, but the point is that this algorithm produces what you wanted, what we started with, and this is the general way that we handle errors. So what are the properties that it has? It will terminate. If there are additional errors later on, it will also handle them. Now the question is, does it handle it in the best possible way? I don't make that claim. What I do know is that it handles the errors that users typically make quite well, and that's what I'm mostly interested in. But I suppose I should do a theoretical analysis of this as well, to be totally honest. 1 minute? Okay, so let's skip that. And let me say a few things about things not said. Let's skip that, let's skip that, let's skip that. Let's talk about the accumulator. One of the annoying things about LaTeX, 6 minutes? Oh, okay, so I have time.
Until your slot is over.
Pardon me?
Until your slot is over.
Yeah, okay, very good, okay. So I think nonetheless I'm gonna, well, let me backtrack just a little bit. Things not said, I'm not going to talk too much about them. I want to talk about what's important. Okay, yeah, this is what we want to talk about. So one of the annoying things about LaTeX is that in order for everything to come out right, if you have cross-references, if you have a bibliography, you have equation numbers, et cetera, references to other equations, you need to run LaTeX at least twice, okay? Because what it does is it writes a bunch of information into an auxiliary file, and then it uses that as an input when you run it the next time, okay? So it would be much nicer if every time you add a character or delete a character to your document, that all that stuff is updated, okay? And this is what the accumulator does. It's the last stage in the pipeline. It's after parsing, but before rendering. And what it does is there's a function that walks through the syntax forest, builds up a data structure called the accumulator, and uses it as it goes to update the blocks. Like, for example, actually put in the right section numbers, okay? And it's a big record. Well, let me say, I guess, a typical example of where it comes from. If I have this text somewhere in the document, something about steam engines, and I cite some reference, NE, and if later, at the end, I have a bibliographical reference referring to NE, something about Newcomen engines on Wikipedia, these things have to be reconciled, okay? And that's what the accumulator does. The data structure for the accumulator is this huge record. And what I did is I was developing this every time I needed to reconcile some other stuff, I just added a field to the accumulator. So for example, this is the one that deals with cross-referencing, things like what you saw with the Newcomen engine. This is how you do footnotes, or what actually turned out to be endnotes, because there's no such thing as a page in HTML. This is what is used to store the macro definitions that you have made. So you see, when you parse it, it sends this to the accumulator. It figures out all these macro definitions, and they are used in the process of walking through the syntax forest. Okay, so okay, I think I have time for this. 3 minutes, okay. So there's some kind of wild functions that you use to do this. There are 2 helper functions, update accumulator. It takes an expression block and the accumulator record, and it updates that record with the information that it extracts from the current block. There's a companion function called transform block that takes the info in the accumulator and transforms the expression block accordingly. Like maybe it already knows what the section numbers are, or some cross-referencing thing. And these things are sort of melded together. They sort of operate in tandem through the function transform block, which takes the accumulator record, all this info that has been extracted, and an expression block, and it returns an updated accumulator and an expression block. And it does it by, first of all, updating the accumulator to get a new accumulator, and then using that new one to transform the block. Okay, I'm not sure I should have done this. Anyway, this whole process is orchestrated by a function, transform accumulate tree. It's a function that allows you to walk through the entire tree, transforming both the accumulator and the blocks at the same time. Okay, so very quick demo, and then that's it. We'll go to this little micro LaTeX demo once again, and I'm going to edit the text, and I'm going to show the table of contents, which is part of the stuff that the accumulator makes, and I'm going to change something or other. I'll do something stupid here. Okay, I have this section, a two frequency packet beats, okay? And I'm just going to replace that by beats. And, well, I can't spell, of course, but you get the idea. As I typed that, it both updated, I'll do it again so you can believe me, it updated the beats in the document, and it also updated in the table of contents. So this is sort of the general shtick, is that all this stuff that you would normally do by running tech twice, you can do by just typing away, and the system will handle it for you. So that's the end. The idea was to have a system that would give you instantaneous rendering and handle things gracefully, and so I could make nice things for my students. So thank you very much. Any questions? Yes.
The whole thing about handling errors is very dicey because there's lots of different interpretations of undefined states.
Yes.
You might guess what the user meant and guess wrong.
Right.
Here's a catastrophic case. Well, what do you do? Render giant question marks?
Yeah. Yeah, I struggled with that, and I still struggle with it to some extent. And what I decided to do was to do something that I knew would work in the sense it would terminate, and it would handle sort of the typical errors that users make in a way that made sense. I'm not making any claims that it handled. Certainly, it will handle all errors, but it may not give you nice looking output, but it will handle the typical errors nicely. Yeah.
Is there a way of looking at your document and saying render with no errors or render with 5 errors with a certain percent of?
I haven't done that, no. No, but that would be an interesting thing to try, yeah.
I think once you have an error, then you're just sort of doing your best.
Yeah, you do. The main thing is I view it as try to give good feedback to the user. And when I'm editing, what I do is I'm looking back and forth, and when I see an error, I try to correct it immediately. If I made many errors and then went back to correct it, then I might have exactly the kind of mess that you were speaking of.
Well, the nicest thing about this is that you can see right away when you have it.
Exactly, yeah.
So, and this is the beginning. Is this available?
Yeah, it's at scripta.io. Scripta, like, scriptorium or something like that. And
Many years I'm back playing with LaTeX.
I'm sorry, say that again?
After many years I'm back working with LaTeX.
Aha.
This would be very nice.
Well, give it a try, and please tell me about what doesn't work, because it's, I don't think it's ready for prime time yet, but it's getting better.
All right, well, my collaborator, Alan Brown, is deep in this stuff. So
Yeah,
I'll
yeah.
pass it on to you.
Okay, very good. Are you a mathematician?
Computer scientist, I guess?
Well, that's a form of mathematician.
Yes.
Yeah. Okay. Yeah, by the way, just a personal note, I as I said, I worked in many programming languages for many years, but when I discovered functional programming, I had this Rip Van Winkle moment, because I had never seen anything like typed functional programming, and it was just wonderful. And I felt like a guy who had fallen asleep for 100 years and awakened, and progress had happened.